Hi everyone, welcome back. In this section we're going to look at another kind of product for vectors, and this is known as the cross product. So unlike the dot product from last section, where it took two vectors in and produced a scalar as an output, the cross product takes two three-dimensional vectors in. It's only restricted to three-dimensional vectors. It takes two three-dimensional vectors in and produces a three-dimensional vector as output. So we also refer to this as a vector product, because vectors come in and a vector comes out. So just like we did with the dot product, we found a concrete motivating example of why we might be interested in a dot product, and that was in terms of the angle between two vectors. The dot product helped us compute the angle. In this context, with the cross product, it turns out that there's a relationship between the cross product, which we will define shortly, and the area of the parallelogram determined by two vectors. So let's get a feel for this area problem. So we want to find the area of the parallelogram determined by these two vectors. So we got the vector A, which is 3, 0, 4. So here it is as a position vector. So that's our vector A. And then we have this vector B, 0, 4, and 3. So there's B. And we're interested in the area of the parallelogram determined by these two vectors. Let's get a visual for this. So here we have our two vectors sketched in our three-dimensional space. The parallelogram determined by these two vectors is shown here, and that's what we're interested in finding the area of. If we look at it from the right angle, it actually will start to look like a parallelogram, so we're looking at sort of from a top-down view. That's what we want to find the area of. Now, the way we find the area of it is just as we would any parallelogram if we know some lengths and the angle between the two sides. So in this case, our picture looks something like this with a little bit of maybe perspective drawn in. So there's our parallelogram we're interested in finding the area of. Let's redraw it. So it's going to look something like this if we redraw it sort of flat. We've got a vector A, we've got our vector B, and we're interested in finding the area of this. If we know the angle between A and B, then we can use that to find the height. The height of this parallelogram would be the length of A times sine theta. And therefore the area would be the height times the base, just basically the area of a rectangle. And we can imagine just chopping off this triangle, moving it to the other side, and filling in sort of the gap over here with that triangle from the other side to turn it into a rectangle, if you want to think about it that way. But the idea is the area of a parallelogram is its base times its height. So it's the length of A times the length of B times sine of theta. And we already know that from the dot product we could find the value of the angle theta and go ahead and work out what the area is in this case, but we'll find out that this cross product is much more tied in nicely with the area of a parallelogram. So we'll dive into the definition of the cross product and we'll see how it's connected with area. So what is the definition of the cross product? The cross product, or vector product, of two vectors, and again we're restricting just to three-dimensional vectors, that's the only dimension that this cross product is defined in. We've got two vectors A and B. We define the cross product to be this new three-dimensional vector where the three components are given by these difference products of the original components. You can notice that the first component of the cross product only depends on the second and third components of the original two vectors, and similarly down the line. The second component only depends on the first and third component. The third component only depends on the first two components. So we get each component of this cross product by considering some difference of products of the other components. There's a nice memory device for remembering this formula, and it is in terms of determinants. So what is our memory device for the the cross product? It is as a determinant of this sort of formal matrix. Formal matrix because I'm actually using as some components in this matrix the standard basis vectors, which are not scalars, which are not numbers. These are vectors, so it's not necessarily a matrix here, but it's just a nice memory device. So what I'll do is I'll put as the first row the standard basis vectors I, j, and k. The second row will be a1, a2, a3. The third row will be b1, b2, b3. And I've got these vertical bars around this because that means determinant. So how do we compute a determinant? This is something you will have seen in Math 232. If you haven't got there yet, you soon will see that in Math 232. Again, this is just a memory device, so if you haven't seen determinants yet, then you just refer back to the original formula that we've got up here in the definition, and that's how you compute it. This memory device is just a way to remember that formula. So the memory device says you want to compute this determinant. How do we compute the determinant? Well, we can do an expansion along the first row. And so what I'll do is I will take this value I hat and multiply it by the determinant of the 2 by 2 submatrix. So we get the determinant of A2, A3, B2, B3 times I hat, and then we do the same thing. Now we take away this term, j hat, and multiply it by the 2 by 2 submatrix with this column and this row removed. So that would be negative the determinant of A1, A3, B1, B3, and that's j hat, and then added to that a similar thing with this last component, k hat. So we remove that row and that column, compute the determinant of that, and multiply it by k hat. So that would be A1, A2, B1, B2, k hat. Where one of these 2 by 2 submatrices, and I'll just write it as in general form capital A, B, and C, and D, where this 2 by 2 submatrix determinant is just obtained by taking A times D, so the diagonal elements multiplied together, minus the off-diagonal elements. So that's our memory device for remembering the cross-product formula. And so that means this component here, we would get by multiplying A2 to B3 minus B2 times A3. So that is A2 B3 minus A3 B2. And that's exactly that first component. And then for the next component, we've got minus, and then the 2 by 2 determinant here, which is A1 B3 minus A3 B1. And then lastly here, this is A1 B2 minus A2 B1. And the key part is that middle term, because if I look at this middle term, A1 B3 minus A3 B1, there's that extra minus sign out front as a part of this determinant formula, which we're using as our memory device, and that's causing the order to get switched here. So you can see it's A3B1 minus A1B3. Alright, so that's our memory device for remembering the cross product formula. We'll do some examples where I use this memory device and we get used to computing a cross product. But before we do that, let's just list the main properties, the main defining properties that a cross product has. So it takes two vectors in and it produces a vector as output. What properties does that output vector have? Well, it turns out that the vector has two defining properties. And these two defining properties are really about what a vector consists of. It's a quantity that has a magnitude and it has a direction. So the first thing is, the defining property of the cross product is about its direction. Where does it point? Which direction does it point in? It turns out it points in a direction that's orthogonal to both of the original two. Now if I have two vectors originally, maybe I'll use my two pens here. If I have two vectors, then there are really two directions that are orthogonal to it. There's this one direction sort of coming out this way, and then there's another direction that's coming out the other way. In other words, there's this whole line that's perpendicular to these original two vectors. So which one of the two directions is our choice for the cross product? Well, it turns out it's given by the right-hand rule. And that's shown in our diagram here. I've got our vector A and our vector B, and we take the cross product. There's really two possible vectors that are perpendicular to A and B. There's one that points down and the one that points up. The question is, which one of those is going to be the cross product? And it's the one given by the right-hand rule. So you take your right hand, you point your fingers in the direction of A, you curl them in the direction of B, and our thumb is pointing in the direction of the cross product, and that's up in this case. So that's the first defining property, is that the direction of the cross product points in a direction that's orthogonal to both of the original vectors given by the right-hand rule. The next bit is, how long is it? What's its magnitude? It turns out that the magnitude is equal to the area of the parallelogram determined by A and B. So in terms of our diagram here, we can sketch our parallelogram in. The area of this parallelogram, whatever that is, that ends up being the length of this vector. That length of the cross product is precisely the area of the parallelogram. So those are the two defining properties of the cross product. It's a vector where the magnitude is given by the area of the parallelogram and its direction is given by the right-hand rule, and it's orthogonal to both of the original two vectors. So let's do an example. We've got two vectors A and B. We want to find their cross product. So we're going to go A cross B is equal to 5, 7, 0 cross negative 3, 4, 2. So we can use our memory device to do this cross product. Maybe I'll write that in here. Our memory device is going to be, take this 3 by 3 matrix, this formal matrix, so this first row consists of the standard basis vector, second row is 5, 7, 0, next row is negative 3, 4, 2. So for the first component, we cross out the first column and first row. We work with this 2 by 2 submatrix, and it's 7 times 2 minus 4 times 0. So that's 14. For the next component, it's going to be negative of, and what we're going to do here is we're going to cancel out first row, middle column, and for that remaining 2 by 2 submatrix, we're going to go 5 times 2 minus negative 3 times 0. So that's 5 times 2 minus, and then negative 3 times 0. So really that just boils down to negative 10. So maybe I'll write that in the next line here. And then the last entry we get by considering this 2 by 2 submatrix, and it's 5 times 4 minus negative 3 times 7. So that's 20 minus, and then negative 3 times 7, so negative 21. So in other words, it's plus 21, and so that has a value of 41. And so there is our cross product, 14, negative 10, and 41. So that's one way to do it with a memory device. I like to do it a little bit more succinctly than using the memory device. I still use it, but I sort of use it in the background. And so this is how I would do it without introducing the I hat, j hat, k hat. I would do it in the following way. I would still, maybe I'll draw a vertical line here. All the ideas that were just present in our calculation are all still here, but I do a little bit less writing. So there's the cross product I want to compute. What I do is I just move the numbers from the second vector underneath the first one. And then we go ahead and we compute the cross product by doing exactly the same product. I say I want the first component, so I ignore that first entry of each of them, and I only work on the second and the third entries, and I go at 7 times 2 minus 4 times 0. 7 times 2 minus 4 times 0, that's 14. For the next component, I have a minus sign that's going to appear there. Cross out that. Now I look at the 5 times 2 minus negative 3 times 0. So that's a minus 5 times 2, which is minus 10. And then the last component, I cancel out that one, and I look at the product of 5 times 4 minus negative 3 times 7. So that's 20 plus 21, or 41. So again, the memory device is still there. I'm still looking at these 2 by 2 determinants, but I didn't actually have to write out the full 3 by 3 determinant. I like this one because it's a little less writing, but all the ideas are there, and it's utilizing the original definition of the cross product. Okay, so the next example asks us to show that for any vector A, the cross product with itself is 0. So for any vector A in V3. V3 just means the vector space of 3 dimensions. So that's the set of all triples, vectors that have 3 components. So how are we going to do this? Well, we're going to start with our vector, our arbitrary vector, which is A1, A2, A3, and we're going to cross it with itself, A1, A2, A3. We can use our memory device that we have up above, or we can use the one that I did on the right hand side and just write the numbers underneath. The idea, if we use the memory device up above, then what we end up with is a 3 by 3 matrix. First row is ijk, second and third rows are identical. And you may remember a result from linear algebra that the determinant of a matrix where 2 rows are the same is going to be 0. So we get that result almost immediately from results about determinants. However, we can see that it's the case by just actually going through the calculation. So I'll write the numbers down there, or the components. And so our first entry is going to be, cover up the first one, so it's A2 times A3 minus A2 times A3. So it's A2 times A3 minus A2 times A3, and that's going to be 0. What's our next component? Well, it's going to be negative of, and I cross out the A2's, and I get A1 times A3 minus A1 times A3. And the last component would be A1 times A2 minus A1 times A2. And so each of those components is 0, and therefore we get the 0 vector. So a vector crossed with itself is going to be 0. Okay. So now we're getting into justifying those properties. There was those 2 basic properties, 2 fundamental properties, I should say, that a cross product has. The direction the vector points in, perpendicular to the original 2, and given by the right-hand rule, and its length was the area of the parallelogram. We're now verifying that these are actually true for the way the cross product was defined in terms of components. So here we're going to show that the cross product is actually perpendicular to A and B. How are we going to do that? Well, we just need to check that a certain dot product is 0. What is it? Well, I want to show that A cross B is perpendicular to A. So I just need to check that A dot A cross B is equal to 0. And I also need to check that B dot A cross B is equal to 0. because two vectors are perpendicular precisely when their dot product is 0. If we use our memory device on this, just to write out what this product would be, I mean, you can go ahead and you can write out the components for these and do this calculation, but I just want to write out what this would be. So the A dot A cross B, the A cross B, we've got A1, A2, A3, B1, B2, B3. With the I hat, J hat, K hat in the top row, we compute the cross product. We get the individual components, the one with the I hat component, one with the J hat component, one with the K hat component. Then when we dot it with A, we are effectively replacing I hat with A1, J hat with A2, K hat with A3. So I can really just say, hey, this dot product followed by the cross product, or the cross product I should say, A cross B followed by the dot product, is really just the determinant of this matrix, and it has two rows that are the same. And if we have two rows that are the same, then the determinant is 0. So you could check it by doing this component-wise argument, or you could appeal to a higher result, something from linear algebra that says, hey, I already know this dot product of A cross B with A is going to be 0 because it's really just the determinant of a 3 by 3 matrix which has two rows that are the same. And similarly for the other one, it would be a B1, B2, B3 as the first row, A1, A2, A3 as the second row, B1, B2, B3 as the third row. And again, since two rows are the same, the determinant is going to be 0. So I'll add the zeros in there. All right, so the cross product is perpendicular to the original two vectors. Let's maybe use that to solve a problem. So find a vector that's perpendicular to the plane that passes through these 3 points. So we've got a point, 1, 2, 3, another point, 1, 0, 1, and another point, 2, 1, 1. Notice I'm not drawing the coordinate systems in the background. I'm just saying we've got these 3 points. I'm not really too concerned about where they sit actually in space. I'm just drawing sort of an abstraction of what they would look like. There's our 3 points. I want to show that, or I want to find, rather, a vector that's perpendicular to the plane that passes through these points. So I've got these 3 points. From those 3 points I can construct a couple of vectors. There's one vector I can construct. There's another vector I can construct. Maybe I'll call this one A and this one B. What is our vector A? It would be tip minus tail, so it would be 1 minus 2, or negative 1, 0 minus 1, or negative 1, and 1 minus 1, which is 0. What's our vector B? Our vector B would be, again, tip minus tail, 1 minus 2, which is negative 1, 2 minus 1, which is 1, and 3 minus 1, which is 2. And now I want to find a vector that's perpendicular to these two. Well, that means I'm interested in a vector like this, where I've got right angles with each of those. And I can get that vector by taking A and crossing it with B, because that will give me a vector that's perpendicular to both A and B. So let's go ahead and compute the cross product. A cross B would be negative 1, 0, cross negative 1, 1, 2. Again, I like to write the numbers down below. In fact, I probably didn't even need to write that line out because I already had them right here situated nicely that I could sort of start to read the cross product off of it because they were already stacked. What's our first value? Well, let's cover up that one, and it's negative 1 times 2 minus 0, so that would be negative 2. The next one is, I'll throw a negative sign in there, cancel the middle one, it's negative 1 times 2 is negative 2, and then minus 0. So I've got a negative 2, and then with that extra negative sign means that we get a value of 2 for that component. And lastly, we cover up this third column, and we get negative 1 times 1, so that's negative 1, minus the product of these two, which is 1. So we get negative 1 minus 1, that's negative 2. And so there is our cross product. there is a vector that's perpendicular to the plane that passes through these points. So this vector is perpendicular to the plane that passes those 3 points. In fact, any scalar multiple of it would be. So I could even factor out a 2 and write it even more simply as, so -1, 1, -1 is a vector perpendicular to the plane that contains those 3 points.